started. Let's pick it up where we left off last time. We'll just talk about these two sampling distributions. Wait. Talk about these two sampling distributions, and we'll try to build some posteriors out of them. One of them you know really well. Hopefully you know what normal distributions look like, where they're centered, the scale, all of that sort of stuff. So we can draw that picture, but I'm going to assume you don't know what a beta distribution is. So that's probably your first new distribution if you haven't played with a lot of probability distributions in this class. We're going to be picking them up as we go. When I introduce you to a new probability distribution and you're unfamiliar with it, your job is to go to Stack Exchange or Wikipedia and read about it. You know, it'll tell you about it in an example real quickly. It'll tell you what the mean of the distribution is, if it exists. It'll tell you about the variances or the moments, if they exist, those sort of things. I'll tell you what the moment generating function is. I'm not going to hold you responsible for knowing those off the top of your head, but familiarity with the distributions will make your job real easy. And I'm going to show you what I mean. So sometimes we don't have to do all the math and work every little detail out in every integration if we know what the distributions are, if we're familiar with them, if we can look at them, recognize them, and then identify their means and variances. So I'm going to try to save you some time. If you prefer to work it all out in gross detail, it won't actually help you. But if that's the way you want to go about business, come midterm time, you'll probably spend 50 minutes working one integral. And sometimes you don't even have to do that. So I'm going to show you the way around everything. I'm going to teach you a new word today, conjugacy. So it's when the prior and the posterior distribution have the same forms. So just write that down. So a conjugate prior and I'm going to give it a name. I'm going to call it pi theta. So I'm just going to start denoting my posteriors and my priors, maybe with the same symbol. So because they're distributions on the same spaces. I'll tell you what I mean in a second once we go through our examples. So I'm going to rephrase this. A prior is conjugate. A prior, pi theta, is conjugate if it's a member of a distributional family I'm going to give this a name. I'm going to call it F, just for family. I don't think I've used F on this stuff right here. It's not the same F right there. F just means space. It's a family of distributions. I'll be real clear about this in a moment. So a prior is conjugate if it's a member of a distributional family F and the posterior distribution is also a member of F. So basically the prior and the posterior are members of the same family. When that happens, we say that the prior distribution was conjugate. So if you've ever taken a linear algebra class, or maybe an advanced analysis class, you'll hear the word conjugate regularly. If you've taken a complex analysis class, you'll hear the word conjugate. All of those classes are using the word differently. I don't have a common root as to why we use that word. So if you guys want to explain it to me, you can, but it doesn't mean the same thing. So it's not taking the conjugate of a matrix or anything like that. So this is a new definition, and it's a similar word to the one that kind of floats around mathematics. There's other words like invariance And that word kind of means the same thing, but you have to tell them invariant to what, and what the invariance property is. So we'll learn that word too, but that word doesn't mean anything until you tell me more about what the setting is. So this word, if you hear a Bayesian use it, the word conjugate, they're probably talking about the prior distribution they're saying they're using a conjugate prior. So let's just look at some examples real quickly. So, a family of distributions so here's just a couple examples. Might be normal mu sigma squared. So what I mean by this is that I have a whole collection of normal distributions. And I've got an infinite collection of them because I can consider an infinite collection of mu's in sigma squareds. Not all normal distributions are the same. Once I lock down these parameters, so once I say that's 5 and that's 1, that's a member of the normal family. So it's a specific distribution. If I just talk about normals and their arbitrary mu's and variant mu's and sigma squareds, then it's a whole collection of normal distributions, and that's the family. If you're familiar with the exponential family, I'm not talking about that. That's too broad. That's families of families. So exponential distributions, normal distributions, they all belong to the exponential family, but that's too big of a family. So I'm talking about your immediate family and not your cousins and not all the people you're related to, but your tight family. So normals are a collection of distributions. Bernoullis are a collection of distributions. Once I lock down what P is, and I just don't use it as a placeholder and I give it a numeric value, then it's a specific member of that family. So what I'm saying is, if the prior distribution happens to be normal, and the posterior is also normal, then we would say that the prior is conjugate. And it turns out, for this example, if I do use a conjugate prior, if I use a normal prior on mu, and I slide it through the likelihood function that I can induce through this sampling distribution. So I take a sampling distribution, I throw all the data into it, I think of it as a function over its parameters, now it's a likelihood. So if I take that likelihood, I multiply it by a normal distribution, it will still be normal. And that's just a bunch of algebra. So we're not going to start with that example because I have to do a bunch of stuff, complete the square, walk you through normals, but we'll see a very close example to that today. So we will touch the normal example. But I want to start maybe with this one right here. So let's just look at this example. We're going to try to build this posterior distribution. The sampling distribution looks like this. So that's the sampling distribution. So I'm going to build the likelihood. So I'm going to imagine that I've got a whole collection of data out of all of this. So I collect not just one x from this, but I collect a whole bunch of x's. Do that over and over again. So I collect cap x, x1 up to xn. I'm going to assume that all of these are Bernoulli. So this is a sequence of ones and zeros. That's what it is. And from this collection, I can try to figure out what maybe good values of P are that generate it. So what we're assuming is that I've sampled from this distribution, and times P never changed. So P's the same thing, it's just a coin flipping model. I'm flipping the same coin with the same technique to flip that coin every single time. I get these values, now I want to build up the likelihood function. So the likelihood is this product. I goes from 1 to n. Call this LP given x. It's proportional to this function right here. This is just p to the xi, 1 minus p. So 1 minus xi. This is p to the sum of the xi's. 1 minus p to the n minus some x's. Draw some indices on there so you can distinguish everything. We'll drop those later, but that's what this looks like. So this is a likelihood function, and we're going to have to picture what this looks like. Keep in mind, p itself lives between 0 and 1. So it's just in that interval, it's a probability, that's how we like to think about it. It's an arbitrary convention, but we all stick with it, so that's that nice. So that's what that likelihood looks like, and we'll look at it a little bit later. The question is what's the conjugate prior? And I just want to write this down for a second. I know probably a dozen of you know the answer right now. So if you've ever seen any Bayes, you've probably seen an example of this. So what's the conjugate prior for p? And what we would look at is pi p given x, this is the posterior distribution, is proportional to p sum of the xi's, 1 minus p n minus sum of the xi's times the prior distribution. I could normalize it if you want. I could write this down like this. Integrate between 0 and 1, p to the sum of the xi's, 1 minus p n minus sum of the xi's, times pi p, whatever this function is, dt. The good news is in trying to recognize if this is going to be a member of the same family as this, I don't have to pay any attention to this stuff down here. You might think, yeah, you do. Pi p is right down here. So it's in there. Once I integrate over this, this is just a function of the sum of the xi's. P's aren't in there. So I take an integral over p. Once I integrate that and I have the indefinite integral, then I'm plugging in the values 1s and 0s for all the p's there, and all the p's are gone. There's no p in the denominator of this equation. So I don't even have to look at this part right here. This is just the normalizing constant. It's the thing that rescales the distribution so it adds up to 1. So that when I tell you what the probability is, you know what's big and what's small. But the functional form of p is all up here. So this is the function and this is the shape. So I like to not do that integral and work through all the normalizing constants because sometimes it can't be done. And in this specific case down here, it can only be done if the hyperparameters in my priors are integers. I can write it down numerically for you, otherwise I have to approximate it. So it's one of those integrals that can't necessarily be written down analytically. So if I can't write it on the chalkboard, it's not analytic. I can still compute it. Number. I could approximate it as close as you want. So the question is what distribution, function of p, can I slide through here and it has the exact same functional form over here, and I don't change the functional form? And there's no way to do this beyond staring at this thing, the likelihood, and imagining what distributions you know that I can multiply by over here and retain its functional form over here. I don't have a trick for you other than knowing distributions. So you wouldn't know this answer if you didn't already know the answer. So somebody help me out. What is the answer? Theta. So how many people knew that? I just want to see where we're at. And then how many people that's a completely new distribution to you? Kind of. A little bit. There was a time I didn't know anything about it. I saw it in a package. I was like, what's that? That's no familiarity. That's 0. I'll call that a 0. It's like, okay, I know this thing exists. Okay, I'll take that as a quarter of the class, but I think it's probably around a half. So let's write down what a beta distribution is and just see that if you happen to know this in advance and all the properties about it, you can answer this question. So a beta density function, when I speak And when most people speak, they'll usually say a beta distribution is. Just keep in mind the distribution is the measure, it's the thing that's adding to 1. I can take a density function and turn it into a distribution by integrating with it. So that's how I go between the two things. So sometimes I say a beta distribution is, and I write down the density. So if that bothers you, it's going to bother you with all your instructors. So it used to bother me when people would do that. Just say it right. And I think I've just listened to too many people say it wrong, and now I say it just pretty loosely. So a beta density function, we'll be polite since this is the beginning of the class, and it looks like this. I'm just going to give it some notation right here. So I'm going to usually, when I talk about a new distribution, aside from everything we're doing on the board, I'll usually present it with a random variable z, just to try to keep us from being confused. So this is a new random variable. I will eventually apply it to that problem and build it on p. So we're going to be building a distribution on p. So I'm going to apply the same functional form to p, but I want you to not be too confused and just know this is aside from it. So this is a standalone 3-minute illustration of what the beta is. So it looks like this. There's 2 parameters that underline this distribution. So 2 parameters. I will say when we use a distribution as a prior in a Bayesian analysis, most people refer to the parameters that underline that distribution as hyperparameters. So we rename them hyperparameters because usually the parameter of interest is what we're building the posterior on. And then there's parameters that determine our prior. We don't want to call them all the same thing. So right here, it's fair to call them parameters, and later on we'll be referring to those as hyperparameters. So this looks like this. I'm going to write down what it looks like up to proportionality, because this is the only part you really need to know to do this problem. So this looks like this. Z to the alpha minus 1, 1 minus z to the beta minus 1. And z is going to live between 0 and 1. And these are going to live between not including 0 up to infinity. And that's going to be both of these. So they live in that range. They're positive numbers. We'll talk about what they mean and get an intuition for it, but it's a function that looks like this. If I replace that with p's, it would look a heck of a lot like that, which is convenient. And so if I multiply it together, it would retain the same functional form. So how do you do that? You have familiarity with the distribution and you practice these things. If somebody asked me what's the conjugate distribution of something, and I didn't recognize the functional form of the likelihood, I wouldn't know the answer. So I have to investigate and see if anybody else knew the answer. And then maybe derive a new distribution. I could probably figure it out and see if it existed. And people already talked about it. There is a normalizing constant in here. So all this stuff that I'm leaving out, if I were to write this, this is the normalizing constant right here. I'm going to write it down as inverse of this thing and give you a definition for what this is. So this funny thing I'm writing down here is just this. Z to the alpha minus 1, 1 minus z to the beta minus 1. And then I integrate over z right here, and this goes between 0 and 1. So this is just a normalizing constant. So I compute this number right here, and I divide by it so that it normalizes it and makes it so that everything adds up to 1. That's what you do for any distribution. If I give you the numerator, you can work out the denominator. As long as I give you all the functional stuff that includes the random variable. This is called a data function. And this can be written down using gamma functions. If you know that expression, gamma alpha times gamma beta divided by gamma alpha plus beta. I don't think that's going to help you in this class or on test, but we want to familiarize ourselves with it. So Wikipedia will tell you all those things about data distributions. But really, I just need its form. right here. So this is a beta function. There's a hyperparameter in here called beta, and this is a beta density. So lots of betas floating around. All those betas mean different things. So don't be overly confused. Why do they use a beta for the parameter in a beta distribution? Just to make sure you're paying attention. Why do they call this a beta function? Just to make sure you're paying attention to everything. Which betas are there? So lots of betas going on here. But that's what a beta density looks like. It lives between 0 and 1, and we're going to look at it. But if we did open up Wikipedia or something like this, we would see there's values between 0 and 1, and this distribution could do this. It could be a straight line. It could look like this. It could look even more like that. It could do this on the other side. It can go even higher. And it can even do things like this. So all by just changing what alpha and beta look like. So values of alpha and beta will make this thing jump all over the place. So it has lots of flexibility and probably more than you're aware. I'll also mention that if I crank alpha and beta extremely high, bigger and bigger and bigger, and I make them the same numbers, this thing will concentrate at 0.5, and it'll start looking more and more normal. So it starts limiting to something that looks like a normal distribution. So if you're used to solving this problem and telling me what P is by using X bar as your estimator, and you invoke the central limit theorem, you're taking a step too fast, invoking normality too fast. They teach people to do it in Stat 101 because it's an easy thing to do. And if it were 1930s, that's probably what we would do. But nowadays, we can actually compute and use things like this, and even if it's limiting to a normal distribution, it might not be quite normal for a while. So when the sample size is low, we're going to see the shape looks very unnormal, and later on it's going to look more and more normal. So in our simulation, we'll see that.
So you use that it converges to normal?
Yes. Except, well, okay, no, because of the boundaries, 0 and 1, but inside of the boundaries, it starts looking more and more normal. So it'll get really peaky, it'll have exponential decaying tails like a normal distribution, but you'll always have this little truncation. I like that truncation, because I hate when people invoke the normal distribution on a binomial thing and they say, oh, the answer's, something that it can't be, bigger than 1, less than something. I don't really like that. You shouldn't be talking about probabilities of things when we know that they can't exist. Of course, in terms of engineering and approximations, if n is big, you're probably very close. If n is small, you probably don't. Okay, so we're going to use this and just replace it right here. Right here. So I'll just rewrite this, give myself some more room. Rewrite everything that I have. It's going to be proportional to our likelihood function times our prior. That's Bayes. In a nutshell, parametric Bayes is just likelihood times prior. Which prior, and whether or not you can justify it, that's what the class is about, for the most part. So we'll just replace these terms right here. So I'm going to use the conjugate prior. So I'm going to first have this part, the likelihood, that's p to the sum of the xi's, minus 1. Oops, that's too fast. 1 minus p, I'm building the posterior already. 1 minus p n minus sum of the xi's, that's just likelihood. And then I've got p to the alpha minus 1, 1 minus p to the beta minus 1. So this is the prior. We'll see that it's conjugated in just a second. The likelihood. I really like likelihood functions. So I think there's been too much argument on things like, well, Bayesians need to assume they know something up front. Everybody knows something up front. The driving force of a Bayesian analysis, if it is just your prior, you will convince nobody. It's It's got to be mostly the likelihood driving everything. So this is what this looks like. And if I just product this together, this looks like p to the sum of the xi plus alpha minus 1. I always keep that -1 out in front right here. I never try to tuck it into anything. If I've got a 5 over here, I don't make this a 4 by subtracting off. I leave the -1 because that's how I recognize what the parameters underlying the distribution are. So I want it to look like that. So always leave that 1 there. Nicely, the prior just brings it in for you. So 1 minus p, n minus sum of the xi's plus beta minus 1. So I would have called this thing over here a beta alpha beta. So if I were just writing that distribution down, I can recognize exactly what this is right here just by looking at that form. So I'm no longer looking at just the prior or the likelihood, but I'm looking at them together, and I recognize this looks very similar to that. P lives between 0 and 1. It has this same algebraic form. And here are the parameters. Usually, I don't like to re-nickname this alpha and beta because I already got an alpha and beta. So I like to call it alpha tilde and beta tilde, my updated parameters. And so this thing right here is a beta with alpha tilde being equal to sum of the xi's plus alpha, a little bit from the prior, a little bit from the likelihood. Beta tilde is equal to n minus sum of the xi's plus beta. Again, bunch from the likelihood, a little bit from the prior. And we can even kind of see it when we write this thing down. How much weight does the prior have compared to the likelihood? And it's really nice these things are being added together so we can think of it all very linearly. And it depends on how big that number is. So if I have a lot of samples, we'd be thinking that the sum of the xi's might be getting big. Depends on what p is, of course. If p is entirely small, and we never see this being a big number, that could dominate it, and it would have most of the influence. Same thing over here. This is your number of failures, and that's the contribution from the prior. And so they're relative to each other. The likelihood and the prior being superimposed together to give you something, and we have some inclination to think that the data component should speak much, much louder than the prior. So what we're probably thinking is we want small values of alpha and beta so that it doesn't overwhelm that sum. So that's, again, just some intuition. That's a beta distribution. Let's just write down some stuff about betas. Does anybody see it? Let's just write down a few things about the beta. I want to use this same form right here. What is the expectation of z? Just going back to our old aside notation, new random variable, just talking about a beta distribution in general. I like to do this to remind myself this is going to be a function of alpha and beta. So an expectation is never a function of the random variable that gets averaged out. What do I do? How do I get this? I take z, I take this function, f of z, given alpha beta, dz, integrate between 0 and 1. It's going to be a number. It's not a number that has to do with z, because I've integrated it out, and anywhere I see that number after I work through the indefinite integral, it gets replaced with ones and zeros, with bounds. So what is this? Does anybody know off the top of their head? Alpha over alpha plus beta. So those of you that don't know, that's what a PhD student in statistics looks like. You know beta distributions, we play with them, we're familiar with them. So 2 years ago, Dylan probably wasn't sure. So now he knows. So you bake that stuff in by looking at it over and over again. So do you know what variance is off the top of your head? Alpha beta over alpha beta. you're right. That's amazing that you can do that. I will not ask you guys for that. If I need you to remember something like that, I will just tell you on the midterm. So if I ever conjure up a problem and you go, well, this would be really easy if I just knew this thing, it's because I forgot to tell you what it is. You come up and ask, and I'll tell you what it is. So if it's something like that. If it's this, I'm going to say, nah, you got to know that. So if alpha and beta are the same, there's a certain symmetry in this function right here. These are the failures. These are the successes. There's a symmetry to it. So if the numbers are the same, that's going to be the half. And that's the way that works out. And so it's going to put everything in the middle. If I crank up beta, I'm going to lean everything towards the failures. If I crank up alpha, I'm going to lean everything towards the successes. If I make them the same numbers, I'm going to stack mass in the middle. If I make these numbers big, it's going to concentrate the mass in the middle even more. So here's an example of a beta distribution. Alpha is equal to beta is equal to 1. So this one's a little bit different.
Can you just explain what that E quantity is again?
This is the expectation. So the average value. So if I were thinking about this distribution right here, it's something between 0 and 1. It's where I stick my finger to balance this if I thought everything were weight. So if you've ever taken a physics class, it's the center of gravity.
Is it common to use the beta distribution for the more triangular shape, or is it usually in some variation of the form?
It won't be triangular per se.
Yeah.
So it's curvy, it's rounder. Sums of two betas with parameters 1, 1, i.e. uniform distributions, that's a triangular distribution. So the sums of betas can have little spikes in them. That's kind of cool. Anyway, that's what a beta distribution is. You could work out the variance if you wanted to. I think that's beyond the scope for today. It won't help us. It's a cool algebra problem. If you want to work through it, I think that's a good idea. You can check to see if you know how to do this integral. A lot of times I'm just asking you to recycle it. If I want you to know how to work out an integral, I'll be very clear with you and say, this is coming up. And I'm going to check to see if you know how to do that. And you're going to go, oh, it just says it's going to be on the exam or on a future quiz. I'll remind you over and over again what that means. Okay, so we just worked out our first posterior distribution. That's beta. That's cool, and it's kind of like, well, that's neat. I can work out the expectation of this thing. I think if we left it on the chalkboard, we'd feel real underwhelmed about what the Bayesian's actually doing. So I could work out the expectation for this thing. Expectation of P. I oftentimes just write conditional on the data. So this is the posterior expectation. I usually write just conditional on the data, and most people will do that. Of course, this is going to be a function of the hyperparameters underlying the beta prior, alpha and beta. So it's a function of those, and you usually won't see people write them down. But if you're ever curious what their hyperparameters are, and you're in a talk and people aren't talking about them, throw your hand up and say, which hyperparameters did you choose? And if they say it doesn't really matter, make them explain that to you. So, convince me. I just picked one, it doesn't really matter. There are cases where it absolutely matters. And if you just pick it willy-nilly, it's going to drive your whole analysis. And there are cases where it barely matters. And we're going to see examples just like that, so I'll tell you some of them that you should go in and ask people about this and not that. So we'll just keep them down here, but eventually we'll just get rid of them. We'll know that they're always there. So how would I compute this right here? Again, I just take P, pi P, given X, that's my posterior distribution. I would integrate between 0 and 1, and I would integrate with respect to this. So this thing right here is pi P, given X. So that's our posterior distribution, that's the notation that we developed for it. So I could work out this integral, or I could just use what I know. about everything. So I know what the answer to this is. This is a beta distribution with these two parameters, alpha tilde, beta tilde, that I just worked out. So again, I'm not really doing any math. It looks like I'm doing a bit of math, but I'm just pattern matching. So I know what that is, so I know what this expectation is. It has that form, it's a beta distribution. So I replace P in here with Z, but now I've attributed some meaning to this particular beta. So this is alpha tilde over alpha tilde plus beta tilde. And that looks like this. Sum of the xi's plus alpha over alpha tilde plus beta tilde, we'll write it down in its full blown glory. Sum of the xi's plus alpha plus n minus sum of the xi's, how convenient, plus beta. So I have a little bit of cancellation downstairs. Cancel those out. And this right here is the sum of the xi's plus alpha over n plus alpha plus beta. That's our posterior mean. So our posterior mean looks awfully similar to this creature. Sum of the xi's divided by n. I go from 1 to n, of course. Same thing as always, but that's just the arithmetic average. So back in elementary school or 7th grade or somewhere around then, people told me about statistics and that's all they told me about. Some things I divide by n. Seems like a good idea. In this class, we'll learn more about this and see it be derived. So as n goes off to infinity, as n gets bigger, this sum gets bigger. Keep in mind this is indexed between 1 and n, so I'm summing n things. So as I sample more and more from the distribution, and p is not 0, this will be climbing. And it will overwhelm that. And n will also be growing. It'll overwhelm those. So this is converging to the average. So again, we have another way of thinking, probably alpha and beta shouldn't be too tremendously big. And you might also be thinking, this seems like an awfully compelling choice, a prior distribution that's flat. And it means that I'm not placing any belief weights anywhere else in the space that's higher than anywhere else. So it's all the same. Let me just ask you, is that a good idea? Who thinks it's a great idea and that's what they should do? I don't know if it's great, but it's not a terrible idea. It doesn't seem all that wrong. Is it optimal? It turns out there's a better choice out there. And we'll understand what that better choice means. But if you happen to do this, I probably wouldn't have a huge issue. If you're trying to estimate things near the boundary, if p was super tiny, true p, or true p was super large, close to 1, if you're very big or very small, it can make a difference there. So we'll see that. I'll have to do a simulation study. We can see what the behavior of this estimator is and how it works and how you build intervals. Let me just tell you, I built a posterior distribution, I come up with that. I haven't actually picked values for alpha and beta. But if I did, I would have some distribution that looks like this. Just making this up. So I see some data, kind of looks like that. This is between 0 and 1, kind of looks like a beta distribution. If I wanted to build an interval, the neat thing about betas is I can just use this posterior distribution to do it. I can add up 95% of the mass in here, and I can call these boundaries right here, star 1 and star 2, my interval of where I believe p lives. So keep in mind, I could slide this interval around to the right over here and bunch that to the left, and I would still add up to 95. And I can do that in lots of ways. Confidence intervals are like that too. They're not unique. So what we probably want is the massiest interval, It has the most density in there. We'll talk about that later when we go into intervals and we discuss the comparison between confidence and threshold. Usually I will have done that in the second or third week of class, but I wanted to just kind of take an engineering approach to show you how to do all this stuff before we talk about all the nuances and all the disagreements. So it might work a little bit better if I just show you how to operate before we get into the nitty-gritty. So building an interval out of this, I could build some interval and say, yeah, I think P is somewhere around there. So conceptually, it's easy to use. Let's just do one more, just real quick before we jump into the simulation study. I want to show you next time that this is true. But I'm going to say, we looked at the normal example. I'm going to take a quick shortcut. I'm going to say we're going to do inference on mu. Sigma squared, I'm going to say, is known. So this is just a number. So no inference on sigma squared early on. We'll build that analysis up. Chris?
Yeah, I was wondering, like, if you could talk a little bit about the theories. So, like, we know that size are Bernoulli, and we know, like, we can estimate P with just a mean. We did all these steps, all this math, conjugate to estimate it instead. We get, like, a pretty similar way to do that. Yeah, like, theoretically, like, like, can you talk about pros and cons and these different
Probably. I will. So I want to just go over this example and then iterate that. So I'm going to be talking about that throughout the whole class. So I promise you we're not done with the example. So yeah, we just have an idea what to do. We don't know if it's a good idea. Chris wants me to justify. I just want to operate a little bit more. Just do some calculations. So just normal example, I'm going to do inference on mu. I will point out, I could do this right here. I can just write down f of x I, given mu and sigma squared, and build up the likelihood function. So that's my likelihood. This will always work for me. I can write this down is 1 over 2 root 2 pi sigma. I'm going to power this up to the nth power. That's the normalizing constant. E to the minus sum xi's minus mu squared over sigma squared. And I like to pull my 1/2 out in front of there. So, and that's the normal distribution. I'm just producting it together. So I producted all that stuff together. And then I slid my sum into the exponent. So I could write that down. And you could distribute this sum. Keep in mind, I don't need any of this right here because I'm going to assume I know sigma squared, and I'm just looking at functional components that contain mu. That's the only part my eye is focusing in on, and so my eye is focused in on this. I will show this next time. If you want to get a head start, please do. This is proportional to this. Sigma divided by root n. I just made up that root n. Don't worry right now about it because it doesn't have the functional form. This is correct. I'll tell you about it a little bit later next time. We just don't have enough time. This is x bar minus mu sigma squared over n. So in terms of mu, not in terms of the sigmas are off. You can see it out in front right here. The sigma's powered up to n powers. I've only got one sigma in here. It's scaled by root n. If you know the transformation I made and why I made it, awesome. I can explain that in 10 minutes at the beginning of class next time. The point is that this part right here, it's circled right here, they have the same shapes in terms of mu. The reason I wrote it down this way is it's really easy to work out the posterior distribution. I'm going to do something a little bit weird. So I'm not going to ask the question of what is the conjugate prior. I'm going to do something you've probably seen a lot of Bayesians do. And they do things like this. So I'm going to be polite and put that notation of sigma squared in there. So just to indicate I'm conditioning on it, I'm assuming I know it. And this thing is going to be proportional to 1 over root 2 pi over sigma over root n. This is just this likelihood function. E to the minus 1/2 x bar minus mu squared over sigma squared over n. In my prior distribution, I'm going to multiply by. I'm going to be super lazy, and I'm going to multiply by 1. And then I'm going to normalize this thing, and it's already pre-normalized. That adds up to 1. So how do I know? Because this is a normal distribution right here. So if you know about normals, you know that already adds up to 1. So all I did is I multiplied the likelihood times 1. And I said, oh, that's my posterior. And I don't like multiplying by this. And I know that that normalizes, so I'm just going to write this down. Now, I don't like seeing my random variable on the wrong side of this thing. So this was my random variable in the sampling distribution, but Bayesian flips those around. So they're upgrading mu to the random variable by operating through Bayes' theorem. So I'll just spin those around real conveniently so I can recognize this distribution. Why that thing was squared. So flipping it around induced a negative sign that vanished after I squared it. This right here is a normal. It's centered at x bar, and it's got variance sigma squared over it. And that's a distribution I know a lot about. I didn't have to do any math to do that. But probably lots of you are thinking, you just multiplied by 1. What the heck is that? Explain all of that. And I could ask, is 1 a conjugate prior? Dylan says, Chris says no. Let's just check. The functional form of the prior looks flat. It's 1. The posterior distribution looks like a normal. Centered at x bar. They're not the same. One's definitely not conjugate. So what I will show you later is it's the limit of the conjugate prior. So if I wanted to think about distributions with infinite variance, which don't exist, or at least in this case, for the normal distribution, if I blow out the variance off to infinity, that makes it not a normal. But it's an idea, and I'm going to try to justify that idea later. But what I can tell you with is I was able to do everything on the board today just by recognizing distributions. I'm feeling comfortable. I didn't have to complete the square. I didn't have to do any calculus. I made symbols that look like calculus, but I didn't actually do any freshman calculus today. I just used what I knew from the past. We're going to come back next time and look at this simulation, but let's just spend 1 minute and glance at what this looks like. Or not. Do you mind grabbing that light? We'll be done in 1 minute and 30 seconds. This is pre-warned. So I'm just going to think about flipping a coin. Now I built up a function. This function is on the website, so you can look at it. You can play around with this. This is my sequential binomial example. If you say Bernoulli and I say binomial, and we're seeing a sequence of Bernoullis, we're talking about the same thing. This is Bayes. I've got my alpha and beta. Those are my hyperparameters. I need to know how many times I'm going to flip the coin. So I'm going to pick a number for that. And I've got to pick true p to generate the data. And the only place I use true p in this is in my plotting function and generating the data. So I want to show you what this looks like. This is my prior distribution. The dotted line, I picked the uniform. So I picked alpha and beta to be 1 in there. And I just see this posterior distribution forming. This is my truth. I picked p to be 0.4. Let's just do this one more time. I'm going to crank up the value right here to 50 and flip that coin a whole bunch of times. We're just going to see this beta distribution kind of changing. It's changing because I'm updating the sum of the xi's. So I'm either adding a 1 to it or a 0 every single time and increasing n. And we see all that behavior that I told you we'd see. That's starting to look awfully normal, and it's starting to collapse around the truth. It's not the prior that's doing that. It's the likelihood function. So we're going to come back and study this and answer Chris's question about, you talked about some properties about the prior. I just picked one. It does seem to work okay right here, but what are some other choices? And I'm going to allude to some theory that we're going to carve out within the next one. That's what we'll pick up next time. Homework 1 is out. We'll get started on that. You can do homework 1 right away because I've shown you the answer. Right there. If you want to see more of the answer, I'll show you more of the answer. So homework 1 is very similar to just the first couple of weeks of class. I just want you to do it yourself. Thank you very much for your homework. So I'm going to look these over and then I'm going to discuss them probably next time. And then I'm going to give you my version of the answer so we can all be on the same page. And if you want to argue back, we'll have time for that. Thanks, everybody. All right. What happened? There was a banker's cell. Oh, shit. Story of your life. Yeah.
With some of the theories.
Oh, yeah. Just give you something to do. Oh, that's a crazy.
You see, now he's up to 3.6.
I mean, yeah.
I don't know the answer to that. That's a good question, though.
The advisors are like, there's too much work to do here.
Yeah, there is the practicality of it all. How many people do you have? Maybe working until 5 o'clock in the morning every day. It's pretty exciting. Once you get it to work.
It is just that the modules are good. We're not really do from scratch, and most of the factories do. It's just the tax structure and building the modules into the pack.
You build those yourself. You can't change life. That is the game, right?
Because we have some SB relationship.
Oh, right.
Maybe you have an hour.
You make your own checks. You make your own framework, like, honestly, the part for the rear wheel. It takes that. It holds the rear wheel in place, but the frame bike and the swing arm, I call the whole thing the chassis. So, but some people just call it frame.
Like the relevant frames
It's 2 years ago. Take it. What did you call it? KPM.
I know that we were basing on our stock now.
Oh, cool.
But we use.
Yeah, how it goes. We'll hear about it.
It'll be tough here, probably.
Yeah, it's gonna be a tough year. I might see you a lot of days.
Yeah.
Cool. See you, man.
See ya.
Snow, sugar and creamer and coffee.
Yeah, that's mine. You want the nice breads? Happy to share. What a good buy. Just drop it off right there. Thank you very much.
Are you in your office? I emailed you a copy of my homework, but I can run to like the library and return a copy.
I put it under my door.
Okay.
So, just bring it on. I think it's amazing. So,
Like, I'll close because I can like, go to the library or
slide it there. This is pretty low weight stuff, so I trust you. I know you. Don't worry. But don't do it again.
I did send you an email version just in case.
You did?
Yeah.
Thanks.
I will say this class that this lecture that you did in Prince last semester was probably like one of my favorite ones.
Yeah, it's easy.
Because it's easy,
Follow.
and then you see the demo, and you're
Yeah.
like, oh, I think I get it now.
Yeah, it's amazing that just seeing the little Monte Carlo demo. So, one reason to like Monte Carlo is it's an easy way to teach. So, it's also super useful. But, I don't know, that's my great idea is just simulate a lot. Do the theory, simulate it.
Well, with P.4, it looks like I'm underestimating a lot.
Well, See you now.
All right, I'll see ya.
David, how you doing? Obviously, this class is totally a piece